Welcome back to Physics with Miyoshi. I'm here again with my rope or ball on a string. Talk about uniform circular motion again. And one thing about uniform circular motion is that the velocity is tangent to the circular path, and we know that that's true because as soon as we know that there's a acceleration towards the center, because as soon as I let go and take away that force and acceleration toward the center, it flies off in the direction of the motion or the velocity on that tangent when I let go. Oh! So, here we have, we're going to talk about centripetal acceleration today, or this time, again, the speed, the uniform speed that my object travels along that circular path is indeed tangent to the path itself, which means that it's perpendicular to a radius. Today what I'm going to show you is that the magnitude of the centripetal acceleration is v squared over r. If I draw this little triangle over here again and I move this vector from its position perpendicular to its radius and move it over to here, I can see that my change in acceleration is change in velocity is the difference between these two vectors there. And I can see by drawing this triangle and noting that those two, the radius is perpendicular to that initial velocity, that there's a slight angle in there called beta. If I draw this one straight down, it's not parallel to that, but it is, we know that since it was here, we know it's got to be perpendicular to its own radius. Therefore, if this is theta and that's alpha, then we know that this is 90. Oops, what happened to my pen? We know it's 90. So we know that this angle here has got to be theta, because theta plus alpha is 90. Therefore, and this guy, alpha plus beta, is 90. So beta must be equal to theta in this case. Now, if I take this little triangle here, well, there's not a triangle. If I made a little guy there for the delta v, or the change in my vector velocity, then I have this little triangle here. And this little triangle, what it's representing is just this guy over here. And what we want is we want theta to get smaller and smaller and smaller. And as theta does get smaller and smaller and smaller, then I can see that this becomes, it's an isosceles triangle no matter what, but this distance, this vector is always going to be my change in velocity, and it's going to always be an isosceles triangle. But what I notice is if I draw a different triangle representing my radius and the change in distance, that this change in distance, even though it's along this arc, it gets closer and closer to the approximation of v times delta t. And v is the constant speed that we have back here going around. But the distance it travels gets closer and closer and closer to that straight line, and its magnitude would be my speed times my change in time. So what does all have to do with each other? Well, what that means is looking at these two triangles, even though one represents the vector and one represents the radius and the distance traveled, I can see that they are similar triangles, and this would be a right triangle over here, and this would be a right triangle over here. And if I look at that, I can see that I have a sine of this guy would be d over 2 divided by r. So sine of theta over 2 is d over r, which is just v delta t over 2 divided by r. And over here on the velocity, we have the same thing. Sine of theta over 2 is delta v over 2 divided by the magnitude of my velocity. So that would be this change in velocity divided by 2, and then divide that by my magnitude of my velocity, and that's going to give me that equation there. So, since they are similar triangles and my theta is going to be the same, then sine theta over 2 is sine theta over 2, or delta v over 2 times 2 times v, and I just changed this guy to a v instead of showing the absolute value, or the quantity, the vector quantity, the scalar quantity, the magnitude only of that vector, and that's going to be equal to, this guy is going to be equal to that. I just rearrange things just a little bit to make it a little bit neater and cleaner. Is delta v, or v delta t over 2r, and since if I rearrange this equation, I get, because I want to get the acceleration, so my acceleration I know from kinematics again is delta v over delta t. So I rearrange these two equations. I'll bring the delta t over here, I'll bring the 2v over there, and I have delta v over delta t is 2 times v divided by 2 times r, so my 2's are going to cancel each other out or divide out. V times v is v squared, so I end up with v squared over r, or my centripetal acceleration is v squared over r. Well, this is just a magnitude, and I know that the magnitude is going to be v squared over r from this little guy, but I have to remember too that acceleration is a vector, and in this case for centripetal acceleration, that vector is always pointing toward the center, because as I go around I have to change my magnitude of my velocity toward the center a little bit each time to get where I'm going. So, and if you remember my little ball flying off up into space as I let go, we remember that the acceleration has to go toward the center. Anyway, so the centripetal acceleration is v squared over r going toward the center. And that's basically it. I wanted to take you through this mathematical representation so you can see exactly where it comes from, how we get this magnitude of my centripetal acceleration, and just explain a little bit more about what centripetal acceleration is. So I'll give you a little example, mathematical example here next time on Physics with Miyoshi. Thanks for tuning in. See you next time.